Introduce Shmuel Oren for the first talk of today from University of California, Berkeley.
Good morning. Thanks for overcoming your jet lag, showing up early. I'm going to kind of the main point that I want to stress today is the idea of using computation with higher granularity modeling than we are normally used to as a substitute for expanding the infrastructure, with megaflops becoming cheaper and cheaper and transmission infrastructure becoming more expensive. I think that that's a good way to go. And so first of all, the background is obviously integration of renewables is something that everybody is concerned about these days. This is just an example of California and Texas with the targets of California reaching 33% by 2020, which has essentially already been reached, and heading for 50% by 2030. We see a gradual, if you look at the renewable portfolio standards, there is a gradual increase with the amount of renewables that we have in the system. And one of the problems, of course, is that the uncertainty and variability of wind, which keeps the IS system operators awake at night. The fact that wind is negatively correlated with load, so we have to do, again, it takes some effort to balance the system. In California, we also have the famous duck curve, which if you look at the net load by 2020, we have the belly of the duck basically reflects that during the day we have a lot of solar, and that reduces the net load. And there are two problems. One of them is that the middle of the day we end up with overgeneration that we have to deal with. And we also have very big ramps at the beginning and the end of the day. They were projecting 13,000 megawatt ramp within 3 hours. At the end of the day, we actually already reached almost 11 in February 2016. So those are real problems that require, basically, the challenge is that the ISO needs flexible resources. So flexibility is the key issue. How do you make, what do you do with the fleet? How do you achieve flexibility to be able to overcome those challenges of high ramp and being able to change some of the conventional generation so that we can absorb more renewables? So there are several ways to achieve flexibility. One is to opt for more flexible generation, move from coal to nuclear to gas, which can be much more easily moved around. The other one, which I'm going to talk about, is flexible, trying to extract more flexibility from the transmission infrastructure. Of course, demand response is a way to deal with flexibility, and that's, there is a whole research activity going in that area, and storage. That's another obvious way to try to mitigate some of that high variability. So we are going to talk about flexible transmission. And there are several ways to make the transmission infrastructure more flexible. One is topology control, which means basically switch lines in and out to change to redirect flows. The other one is flexible line rating. Recognize that you can run some of the lines hotter for short periods of time using emergency ratings, whenever for as long as you limit the amount of time. And those are the two things I'm talking about. There is also, of course, FACTS, but that is a much more expensive solution because FACTS devices tend to be expensive, and I won't cover that. So let me start with topology control. Some of you may be familiar with that, but the idea of this switching lines in and out, I mean, has been around for quite some time. The purpose, the objective has changed over the years. There is some work about relieving abnormal condition, reduce system losses. About 10 years ago, we started to look at the idea of switching lines for economic reasons. And the first paper, I think, in that area was by Fisher, O'Neill, and Michael Ferris on optimum transmission switching, and it has been followed by a series of papers with Corey Hedman and myself and some of these authors as well. So why, you know, some people don't understand. I mean, you build transmission, why would you want to switch lines off? And this kind of tries to give you a simple explanation. If you have a 3-bus system here, the nomogram of a DC approximation looks like the figure here on the right, and the optimum solution here under these constraints is here. And that would imply that the way you satisfy the load is to dispatch generator A 180 megawatt, generator B 30 megawatt, C 40 megawatt, and that will cost $20,000 an hour. However, if you switch this line off, now this is the nomogram, and now you can reach this optimum solution, which basically will only cost you 15,000 megawatt hours. So the lines sometimes act as a barrier to achieving a more optimum solution, and under certain conditions you may do better by cutting a line out, switching it off, and that will give you a more economic solution. So this is kind of a simple idea that takes advantage of Kirchhoff's laws, and it's actually being done in practice. If you look, PJM has Manual 03, which lists the whole set of lines in order, about 120 switching actions that can be taken depending on what circumstances are and the load realization. New England ISO has also some in their protocol, but those are static protocols that are not trying to optimize in real time. They kind of give you a series of switching actions that you can take depending on the conditions that you are trying to mitigate. And there have been some examples, you know, during Hurricane Sandy, PJM was able to mitigate some problems by switching some lines. The formulation of the problem, if you have a unit commitment problem and you want to introduce switching, the idea is that you can put a binary variable on every line so that it's either on or off. And now you reformulate the, you know, if you use a B theta formulation in DC approximation, you put this kind of a constraint. So when M is a big number, when the transmission line is off, then that's, you know, there is nothing, I mean, this constraint becomes non-binding, and as a result of that, you are essentially relax the flow constraint on that particular line. If it's on, then that you have the regular condition. There is an alternative formulation using PTDFs, which was formulated by Ruiz, and either of those get embedded in the unit commitment, and now you can solve the problem, and this becomes, of course, a horrendous mixed integer program that you need to solve. But as I said, computers are becoming cheaper and more prevalent, so we don't worry about that. This is an example. If you look at the 118 bus and you looking at the you limiting, we always try to limit the branch and bound so that we don't have, so we put here we limit the number of switches to 10, and it's not very obvious where you're going to switch the lines, but this solution that we got, in fact, shows you that we were able to reduce the dispatch cost from about 2,000 to 1,500, so there is almost a 25% reduction in this example in the dispatch cost. And this is the kind of example that got the attention of ARPA-E, for example, and they put some money into that. So we did all kinds of tests. If you can impose n-1 constraint, that will reduce a little bit the potential saving from 25 to 16, but it's still significant savings. And we have several papers on that. We solved for the ISO New England with 5,000 bus model. And basically the result of all that was that ARPA-E about 4 years ago gave us $5 million to try to see if we can scale this idea to commercial level. There was 2 contracts, one to Tabor's Karamanis Associates and one to us, and they are still now working, have commercialized some of the software to look for a switching alternative, and they're selling it to the ISO as a decision tool. The team that I was involved with was Texas A&M, Arizona State, and Berkeley, and we had several industrial partners, and we were able to demonstrate significant savings in the unit commitment by using this idea. What I'm going to do here is one of the things that came up is that even though the other team was able to demonstrate that PJM for a variety of test cases, they could have saved $100 million a year. Apparently that didn't impress a lot of the stakeholders, because they say, well, you're going to do transmission switching, you're going to essentially mess up the FTR market, and we already have problems with revenue adequacy in the FTR market. So this it didn't have much of there was a lot of objection to trying to do it on a regular basis in the day-ahead market. However, everybody agreed that switching would be a good thing to do as a contingency or measure. So if you have once you close the day-ahead market, you have your FTR settled. Now, if you have any uncertainties that get revealed, then you can it would make sense to use transmission switching as a way to mitigate contingencies. So what I'm going to do here, we'll be looking at rather than using the transmission switching as a day-ahead tool to reduce the cost, using the transmission switching as a recourse action in the real-time market in response to realization of different renewable profiles, and try to see how much that would help. And the idea is that we all know that, ISOs have emergency ratings, and they can use transmission switching to mitigate contingencies. The question is, what happens when you account for that in your day-ahead dispatch? So you're using the transmission switching as a hedge against uncertainty, and that's kind of what we want to explore. So the focus here on using a stochastic unit commitment framework. And stochastic unit commitment, some people think that, okay, the ISO is going to solve a stochastic optimization problem. That's not my intention. Stochastic unit commitment can be thought as an idealized way to simulate a two-settlement market. The two-settlement market, which is the prevailing approach in the United States, where you have a day-ahead commitment and then you have real-time bidding, can be thought as a crowd solution to a stochastic programming problem. Because essentially people bid in the day ahead in anticipating uncertainties, and then you have the real-time realizations, and you have a second market. So if you think, so I look at stochastic, two-stage stochastic programming as a way to simulate this market behavior in a two-settlement system, and that's what we're doing here. So this is more like a simulation tool. So this is, again, we had, there is a paper, again, with Corey Hedman and Michael Ferris, where we're looking under n-1, and that was the original way, but here we are looking at the second approach. So the idea in a stochastic, in two-stage stochastic unit commitment is that you look at the problem this way. You have a first stage decision to commit slow generators, the one that had to be committed in the day ahead. Then you have a renewable generation, which gets realized closer to real time. And then depending on the scenario, you have recourse actions, which enable you to respond to the realization of the uncertainty. So this is like a standard decision analytic framework. So in the formulation, we're looking at, we're formulating the traditional constraint, market clearing. It's a DC approximation, line capacities, and then we also put a constraint on the number of lines that we allow switching, because we need to contain, to reduce the branch and bound tree. Generator constraint, we have generation capacity, ramping up, ramping down, minimum uptime, minimum downtime. All these are, introduce binary variables into the formulation. Then we need to create scenarios for wind. And the way we formulated the scenarios, this is taken out of a paper that I have with Anthony Papavassiliou, is we take a data set. We took NREL, has wind scenarios at every location in the United States. And so you look at the time series of 8,700 hours, and you have a realization of wind scenario, and then we bootstrap it in a statistical way by trying to capture the statistical components of that using an ARIMA model. And then we replicate those by using Monte Carlo simulation. We create variants of that base scenario. So the idea is that you start with data, and then you create 1,000 scenarios, and now we're going to use that as the data for our stochastic unit commitment. It turns out that it's easier to do the scenarios on wind speed and then convert the wind speed to power using a static curve, power curve, and which seems to be pretty regularly behaved. So this is the idea. We now go back to our 118 bus test case, and if you look at the problem, this is not an easy problem to solve, even for 118 buses. We have about almost 50,000 binary variables, 80,000 continuous variables, and but we were still able to solve it using Cplex on a laptop in reasonable time. It took a little bit long. It took 8 hours, and that's not realistic for if you're trying to really be, to operate what system operators have to do. So we had to develop all kinds of heuristic, and one of the heuristic that seems to be very efficient, successful, is to use warm starts. So what you do, you pick 1 hour, which is the most loaded, and you do the switching, you solve that problem, and then you start from there. And that seems we were able to essentially parallelize this solution and solve it in like 40 minutes. So that was one way to do it. But in any case, the emphasis here was more to demonstrate the potential. So we haven't developed the best algorithm necessarily for solving the problem. We just wanted to show what potential there is in this whole approach. Again, we use the worm starts using the simplex algorithm, and and then one of the things that we wanted to see is how much you save. So let me skip through that. So this kind of shows the lines that are going to be switched depending on the constraint. So if you're only going to switch the best one line, we found a line. If you're going to switch two, and so on, but once you go to 7, then the first line to switch is not necessarily the same one that when you had to switch only one line. So this kind of gives you an idea of the combinatorics that goes on. And we also solved the problem without any limit on the number of switches. So this kind of shows you the saving. Again, one of the things that is typical in this kind of problems is that it's often, 3 or 4 lines that needs to be switched to achieve most of the benefit, and then you kind of level. So ISOs really like that, because in practice they don't want to switch more than 1 or 2 lines a day. So this is actually a very positive result. And we were able to get in expectation using the stochastic unit commitment, again about 14% reduction. And that by allowing the switches to be as a recourse action. So the question was, where is the saving coming from? And we did a little analysis dissecting the problem, and it comes from reduction of production costs, reduction of startup costs, reduction of no-load costs, and from reduction of load savings. So we can actually dissect the problem and see exactly what happened in the solution with and without the recourse action that the switching allows us, and we can identify the savings that come from just changing different generators, the loading on different generators. This is a reduction in startup costs. So instead of starting one generator, we were able to switch which generator have to be started twice during the day. This is a reduction in the no-load cost, and again showing us for different scenarios what happens. And this was a reduction in the load shedding. And without the switching recourse action, we had much more load shedding, whereas with the recourse action, we were able to reduce significantly the amount of load that had to be shed. So this just kind of gives you a little intuition where the saving is coming from, that by allowing yourself, giving yourself this extra tool in the recourse, you are able to be a little more aggressive and in deploying the slow generators, and that is going because you have other way to mitigate the uncertainty that comes out. So this is again solving the problem. Give some information about the duality gaps that we have to deal with, and as I said, we were able to achieve about 10% in the objective function in 42 minutes. Now, this is something very important. Anybody that is doing stochastic unit commitment, you have to distinguish between what you're doing in the optimization versus what you're doing in the evaluation. So usually you can solve a stochastic unit commitment problem by reducing the number of scenarios significantly. So we reduced the number of scenarios to using some important sampling technique to 10 scenarios. But then once you have the solution, you cannot argue, look at the objective function that you achieve and say that's your objective function. You actually have to run the full set of 1,000 scenarios using Monte Carlo in order to get a true evaluation of the performance. So what you use for the optimization is not the same as what you're going to use for the evaluation. The evaluation has to be much more extensive to get significant sampling of the performance. So we actually ran the full 1,000 scenarios, and in fact were able to demonstrate in the evaluation phase that were achieved about 12%, and that was statistically significant if you look at the distribution of the objective function that you get for every scenario that you are testing. So this is the kind of the and in a way, the way we did it is that this 12%, 12.9% was actually a lower bound, because we have to make certain assumptions on the policy that we adopted in the simulation. Okay, so then we said, okay, does it scale? So I had a visitor, and he came. He had a model of the European system, where we had almost 700 conventional units and a lot of transmission lines. So it was a data set representing a fairly close to commercial level approximation of what a European system looks like. And you know, here with about 1,400 renewable generation, wind, solar, and hydro. So the question was, can we solve it? And so this is kind of the model that we had. It represents, lumps together certain countries, but basically we have France and Switzerland kind of lumping together, and then Belgium, Luxembourg, and so on. So this was a really challenging model, and this shows all the generation unit, buses, you know, the data, and it's actually the person that brought this model he's just finished his PhD in Trondheim, and this is a set of, again, we had a bunch of wind scenarios that we were testing, and the question is, how do you solve it? And we came to the conclusion that, you know, I mean, if you look at the size of the problem, you have 300,000 binary decision variables. So this is a very challenging, you know, maybe I should have called Michael Ferris, but to solve that, but we decided to do our own. But again, the problem is we found out that a way, again, since we wanted to demonstrate benefits, that you can be a little loose, you know, use some heuristics, and what we ended up doing is decomposing the problem into 5 control areas, and limiting the switches, the transmission switching within the control area. So we're solving a problem in 2 stages. You know, you do the unit commitment for everything, but then you allow transmission switching within the control areas, and that worked. You know, we broke up the Europe into you know, 5 control areas that we are addressing, and it turns out that, you know, using this approach, most of the benefit from the recourse, transmission switching recourse, was in France and Switzerland. I don't know exactly why, but it's probably more because the grid there is a little more dense and has more redundancy than in other parts of Europe. So so if you look, I mean, I'm going to skip the whole kind of solution approach, but this is the results. If you look at for each one of the control areas, we're looking at regular stochastic unit commitment, a topology control stochastic unit commitment, and you see in France, by allowing yourself to have that recourse action through topology control, the expected cost was reduced by about 1.35%. Now 1.35%, you know, as Dick O'Neill always has I mean, when you're dealing with electricity markets, you're talking about billions of dollars. Like in the United States, the annual trades of electricity is like $400 billion in energy. So 1% is a lot of money. So, and this is kind of the orders of what you can save. But when you translate it to euros or to dollars, that translates to a lot of money. So we are able to squeeze that amount out of in expectation. So this is what happens when you use topology control, and again we can trace where the benefits are coming from. So in this particular area, you have some reduction in startup cost, minimal reduction in no-load cost, some the fuel cost reduction, expected. So we're looking at the expected generation cost of the slow unit, expected cost of the, and so on. So we can actually break it down and find where all the savings are coming from. Again, this is when you do, if you're comparing a topology control stochastic unit commitment with just normal stochastic unit commitment, again, we can see in this particular, again, trace down the benefits, and we get essentially benefit in almost every aspect. Okay, so this was topology control. The next thing we decided to look at is line ratings. And, normally people solve this optimization problem, assume a constraint on the thermal rating of the line, and some lines have those constraints because based on actually because that's you don't want the lines to sag, and so you're trying to keep it above the trees, so therefore the temperature of the line cannot go above a certain level, and that's dictated by some of the weather condition, the wind, the ambient temperature, and so on. But the bottom line is that the thermal ratings are coming from the fact that you don't want the lines to sag too much. However, in some lines, the thermal rating is more of a proxy for stability. So people impose a thermal rating, but actually what they have in mind is the stability. And usually it's easy to detect which comes from stability consideration and which comes from actual concern about the sagging, because you have to look at the emergency rating. Every line gives you a regular rating, and then they tell you an emergency rating. Emergency rating is typically like 30% higher than the normal thermal rating, and they allow, and the idea is that if you have a contingency, you can run it at emergency rating for about half an hour before you have to make sure to reduce the load. And it accounts on the fact that, lines don't overheat suddenly. There is a thermodynamics that goes on. So if there is no difference between the emergency rating and the line rating, you know that that's not a real thermal rating, that it's actually motivated by stability consideration. But when is an efficiency, a difference, then then the idea is that, okay, we can take advantage of that. And knowing that you will be able to run it at 30% more load can help you, again, to consider it as a recourse action and will affect your first stage decisions. So that's what we are trying to do here, to see, okay, let's integrate that into the unit commitment formulation, the fact that there is a looser contingency ratings. And this is some of the, we went to the literature, and Sigre has a whole technical brochure on how you determine line rating. This is kind of the heat equation that you get, and you see that the change in temperature is going to be affected by the current square times the resistance of the line, and they use, you have all kinds of parameters based on the ambient condition, temperature, wind speed, solar radiation. So there is all kinds of manuals that you can use. But the basic idea is that you get normal limits, emergency limits, and what they call load dump limits. And there are 8 different curves. You know, this is a typical page out of the ISO New England equipment rating, and that you can go and dig through and see. But the idea there is that they try, you know, they will change the line rating on a seasonal basis. So the constraints are being adjusted seasonally or depending on some outside condition. Again, this is the comes out of the Sigre brochure, and shows you how depending on radiation, wind speed, wind angle, ambient temperature, how you would adjust the line ratings that are going into the optimization problem that you want to solve. What we are trying to do is more to be a little more active, to do it dynamically. And so the dynamic rating, we're trying to use it as a recourse and to take it into consideration when we solve the stochastic unit commitment. So again, there are some literature on that, but there, you know, goes all the way back to 1977, where first proposed dynamic rating. Then there is some subsequent literature, not much activity in this area, but there is, you know, something that we had to do our due diligence on. But the basic idea that we were trying to explore is the fact that if you suddenly overload the line, the heat of the line is going to grow like an exponential curve, because this is a linear differential equation. And so we can, in fact, assume that there is going to be, until it hits the temperature, that it's going to take a while. So if you translate it, what that would mean is that you can actually run your constraint by saying, okay, instead of having this constraint, I am allowed to have some steps here, because that's going to, for limited amount of time. So so I can decide when I'm going to relax the constraint and move to emergency rating, and then I'm limited on how long that can take, and then I have some constraint on that. After that, I have to go down, because the line would have to be allowed to cool down. So this adds basically three integer variables or binary variables that to formulating the constraint in this fashion, where you are essentially saying that you have another decision variable on when to start your emergency rating, for how long, and when to stop it, and how long you have to stay cool before you can do it again. And so each one of those becomes a decision variable, and you know, only one of them can be realized, so they have to add up to 1. But that gets into the formulation, and I won't go through the detail, but basically you see we have the same kind of relaxation here, except that this binary variable, and we have many more of them. You see how many indices, and that will complicate, of course, the solution of the unit commitment. Now, this tries to explain why that may be valuable, because in most cases, when you run a regular unit commitment, you'll find something like that, where a constraint is violated for a very short time, a spike, but this violation is going to force you to completely change your dispatch, because if you're not aware that that's only a little blip, and for practical purposes, you can run the emergency rating to cover that, then this will make it will appear as an infeasibility, and that will force you to reroute the power, and that will be much more costly. So by allowing ourselves to formulate the constraint in this fashion, where you proactively take advantage of this ability to run the lines hot for a while, as long as you know what you're doing, it of course makes the problem the problem more difficult, because now you have so many more binary variables. However, you can get some significant gains from that. And so this is again going through some of the analysis. Where is the gain? You know, we did it on the 118 bus system, and it shows how you know, the gains from adding that additional recourse. So now we have two kinds of recourses. We have, and we kind of put them together. One is to cut the line completely. The other one is to run it hot for a while and then cool it down. And so this all comes into the same formulation. So sometimes it's better to cut the line out, sometimes it's better to run it hot. And all that contributes to the flexibility that you have in the second stage to respond to different wind scenarios. So we compare with and without, but basically, let's see if this is the dynamic rating. The other one was just with topology control. Again, the sizes of the problem, now we have 450,000 binary variables. But still, you know, we can solve it on Cplex. In fact, we also had access to a supercomputer at Lawrence Livermore, so we did a lot of parallelization. But for the purpose, you know, these runs were for the papers, and we didn't want to rely, because it's much harder to when you get scheduled on those supercomputers. I don't know what their scheduling algorithm is, so it's very hard to tell how much it really took to solve the problem, to monitor. So that's why we end up doing it on our laptops, where we have much more control. So this is going back to that European model, and we see that, you know, if you recall, again, the main benefit is coming from the France and Switzerland, and the gain, so before we had, just with the line switching, we're able to save about 1.35. Now we have another 0.35 saving. So there is definitely an effect. And as I said, we didn't try to get the best algorithm. So this is just one possible solution, but it demonstrates the capability, and that was the goal of this paper, wasn't to develop the most efficient algorithm, but rather to demonstrate there are some potential savings. So this again, this shows where, you know, kind of tries to illustrate how the savings are coming from. So you have a constraint like that. You see that if you would just running it statically, that would be, you know, this would be the loading of that particular line, and that blip here where it gets over the constraint will essentially create an infeasibility and will force you to redispatch and go and get perhaps another generator or something which would cost much more. So by introducing this dynamic line rating and allowing this temporary use of the emergency, it gives you a way to get around that, and you can do that. Now, sometimes, you know, an alternative way to dealing with those is that people are relaxing the constraint by imposing a penalty. And so a penalty, and that's what a lot of ISOs are in fact doing, by penalizing violation of constraint and making the constraint much more loose, flexible. The problem is that when you put a penalty, that ends up affecting prices, and when you're running the nodal prices. So so by actually recognizing that what you really want is to be able to relax the constraint for short periods of time, that gives you a more direct way of handling that kind of problem. Again, this is just a realization. So let me conclude by saying that what we're seeing here is topology control and flexible line rating can both reduce the operating cost. And the idea of the flexible there is embedded flexibility in the transmission network. I mean, for many years, people like to treat the transmission network as if it's a static asset. And once you build it, that's it. We are looking at it more from the point of view of saying, okay, the transmission network, you of course overbuild it, because you want to take care to make it work under extreme condition. But you have to think of it like a four-wheel drive car, that you have the four-wheel drives that if you want to go in mud or on uphill, but when you're going on the freeway, you should be able to disengage some of the power or some of the what you have, and that's going to save you a lot of fuel. So, so the idea of treating the transmission system as more flexible and trying to take advantage of that is enabled by the fact that we are going to have more granular, more sophisticated algorithms. So essentially we are mobilizing computational power in order to make our infrastructure, to recognize the embedded flexibility of the infrastructure, and that is a better way to go than building more transmission line or trying to expand the infrastructure. So this is the kind of the main message, I think, that we have to, with the computers becoming cheaper and algorithms becoming more sophisticated and faster, that we have to think ahead. I expect, given the evolution of computational power, in probably 10 years, every laptop will have 1,000 cores. So we should develop algorithms, and we should start to think of computational approaches, optimization approaches that take advantage of that capability, and I think that there is a lot of potential there. So that's it.
I'd like one of those laptops. I would really like one of those laptops.
Well, I mean, you look at what you have in the laptop today compared to 10 years ago. So, yes.
Well, it's very good, of course, taking into account network flexibility. I'd like to ask a question. We discussed it in private, but it's worth airing it. It's something that you touched upon towards the end, which is overcoming inherent conservativeness of power utilities. They are very conservative because they want to keep the lights on, obviously, and they just absolutely hate the idea of disconnecting transmission lines, because they say, well, this is what the power system is about. That gives you additional flexibility, that gives you additional resistance to any faults. So no matter how many fantastic simulations you are running and showing the benefits, of course they'll just hate this idea because it's against their guts. So have you had success of actually persuading utilities to implement those ideas in practice and to save some costs?
Well, this is I completely agree with you, and this is one of the reasons that one of the lessons that we learned from our ARPA-E project is that it will be very hard to convince utilities to, in advance, to plan on disconnecting transmission line as part of the commitment. However, they've been, treating it as a contingency measure, treating topology control as, they've been doing it. The emergency rating and they've been doing it. So all we're doing here is saying, okay, since you know that you're going to use these tools in response to contingencies, let's see what it means in terms of your dispatch. So all we're doing is trying to just feed in that knowledge in the day ahead commitment. So we are not telling them to disconnect lines. We're just saying you are going to have that tool. So I think that turned out to be a much better selling pitch. Because they're willing to accept, and utilities are willing to take any suggestion when it comes to how to handle contingencies. So now, whether they're actually willing to translate it to the planning action and say, okay, we don't need to build all these transmission lines because we are going to have that additional flexibility, that's a different question. Yeah. Yes. Oh, okay, you handle that.
Go ahead.
How often do PJM and UISO switch of lines?
They, if you go to the PJM, they actually have like 130 switching actions that they account. Now, how often they deal with that, I'm not sure, but I think that they keep some sort of record. So they use. I know specific incidents. You know, I've been talking to Andy Ott, and he says, "Oh, you know, during Hurricane Sandy, we had this. They actually did switching to maintain fault voltage maintenance problem. So, you know, exactly. I think that they are less eager to tell you that they switched the line for economic reasons. But the point is that, you know, everybody now recognizes that some of the transmission expansions are aimed at levelizing the disparity in the LMPs. So we are now if you look at the FERC orders and all that, we are building transmission lines for economics to actually try to levelize and you know, load pockets and things like that. So if you're starting to build transmission line for economics, you're increasing redundancy in the system essentially, then you should be willing to disconnect them for economics. So that's kind of the rationale. But it's a hard sell. I agree with Janusz. Yeah.
You made an argument about 1% savings is really critical in the system, and it's a bit of a large amount of money. And then on the next slide, you showed that you had optimality gaps of 4%. So can you tell me whether those gaps are due to the existence of a feasible solution or to the lower bound? Yeah.
So I don't know. You know, we need probably. I mean, as I said, when I saw a solution that was feasible and we got 1% saving, I said, okay, we'll take it. But obviously, when you have 4% optimality gap, there is a lot of potential there. And one of the things that we are working on is trying to come up with tighter formulations, like introducing valid inequalities, you know, actually improving the formulation of the unit commitment so that the formulation gives us is closer to the integer polytop, and therefore we are going to improve the gap. I have a slide in some other presentation showing how the California system operator, they did some improvement in their formulation, and they are running their unit commitment now with a 0.5% duality gap. And by switching from 1 to 0.5% duality gap, they've been able to save $23 million in a year. So improving the algorithms is definitely, there is a lot of potential there and a lot of money. Yeah.
Do you have some idea how this switching impacts on the pricing that is done afterwards?
On the pricing?
Yeah.
Well, you know, the unit commitment, as I said, what we are doing here is more, I'm trying to simulate a two-settlement market. The pricing, LMP, you know, kind of, I always consider the two settlement in the United States, they had unit commitment where people are building as a way to, I think it's an efficient solution. You know, there is a lot of hype about all this decentralized decision making, and I'm not a big believer because I think that there are a lot of coordination benefits to be achieved in the network. When you have a system that has so much non-convexities and you have all the potential, you know, this kind of approaches of topology control, this is a coordination tool, and which will not be realized. I mean, these benefits cannot be realized by having a completely decoupled solution. So my view is that the way that market design should focus on is creating auctions with incentives for people to reveal their true cost and benefits, and then use those centralized algorithms to actually optimize, rather than trying to achieve a kind of an invisible hand where everybody is doing, you know, I'm a big skeptic about transactive energy. And because I think that the network, there are all these coordination benefits that are going to be left, the benefits are going to be left on the table if you don't solve the problem in a centralized fashion. Yeah.
Shmuel, you mentioned that the reason you couldn't do this on the day ahead was because of the FTR market. Did you happen to come across a case where a line was congested on the day ahead and you had to, pay the FTR, and then on the next day for all 1,000 scenarios, you switched it off?
You mean that the line is congested on the day
The
ahead,
day ahead, and then the next day you
and then it's not?
No, it is, but that's because you're switching it off for all 1,000 scenarios. So essentially, sort of, is there a per scenario cost for switching a line off? So as to make sure it only happens only in 2% of the scenarios, or can you switch it off for all 1,000 scenarios in the recourse?
Well, you can. I mean, in a regular power flow, if you don't have startup cost and all that, then you can say that you'll never switch lines off if there is no congestion.
No, say there is congestion.
If there is congestion,
the FTR,
I don't have specific examples, but there is definitely, when you start to take into consideration contingencies and all that, we have some counter examples, small examples where you can show that even without congestion, you may still get some benefits from switching lines off. So, because it will change the, some generators can kick in. So once you solve the problem with n-1, it's very unpredictable. You really have to solve the mixed integer problem. I've been trying to develop intuition on that, and it's very high. I'm always surprised. So it's much easier. I'm relying on students to come up with counter examples, all this intuition.
Go back to the scenario stuff. If we are, you have a way of working through all the scenarios in order to determine what the right decisions are at the slow in the unit commitment stage, given what might happen, and given your recourse actions, which you're now adding into the mix. So I'm wondering where the ISO sits in relation to the decisions that they're making in the normal course of events. If you're trying to persuade an ISO to take on board these kinds of approaches, what are they doing in terms of the scenarios? Because that has to presumably be part of their setup.
Well, again, those scenarios, the ISOs doesn't run. They do run some scenarios, but in general, they don't. They rely on the market participants to make this. So ideally, what the stochastic unit commitment solution does is it kind of tries to take into consideration, if everybody was smart and everybody agreed, how would this two-settlement market work? What would be the outcome of a two-settlement market? So those scenarios are reflected in the day-ahead bids and in the real-time bids. So the ISO doesn't do that. The ISO actually runs two-settlement system, and it's the bidders that try to work through everything. The bidders and the virtual bidders that are trying to anticipate all these scenarios.
So in terms of trying to sell this, what you have is a kind of a gap between what you're doing, which is a process which is scenario based,
yeah,
and where they would see the value. Which is
well, I have to convince them that this is a hard sell, that the that the stochastic unit commitment is actually a legitimate simulation of a two-settlement market. But at least I'm not trying to, I don't believe some people are talking about stochastic market clearing, and stochastic market clearing doesn't mean anything. It means that you're going to tell people that sometimes you're going to lose money, sometimes you're going to win money. You're going to do it on average. This is like average justice. Some people go guilty people go free and some convicts, innocent people go to jail. On average, it works out. So yeah, that's a gap that we have of trying to recognize that a stochastic unit commitment is actually a legitimate simulation of a two-settlement market.
Well, on that note, I think we're going to have to cut off the questions because time for our next speaker.
Thank you.